Right, good evening, everybody. Tonight we are looking at inductance and inductors. I wonder if I show you what I'm reading, then it maybe might make a difference. Right, they say a typical conductor consists of a coil of wire which may be wound around a former, like a piece of plastic, or self-supporting. They call it the air coil. And when current flows through the wire, it generates a magnetic field like an electromagnet. And then, of course, when when the power is released or the current stops flowing and it's disconnected, then the magnetic field collapses, and that collapsing magnetic field generates also a voltage, and that voltage can exceed the original voltage applied. And they name that self-inductance because it induces a current when the voltage is removed. There they've got a nice circuit for us explaining this is a battery switch. The current flows from when the switch is closed, the current flows through the coil, creates a magnetic field. When we open the switch, that magnetic field collapses and it generates a voltage which gets pushed out and then into the circuit. Now the battery decides how fast the magnetic field is created, and there's nothing that stops the magnetic field when it collapses. So it can collapse a lot faster, and then of course the faster you move the coils through the magnetic field, the higher the voltage, and that's why the voltage that uh, is generated by the collapsing magnet field could be a lot higher than the initial voltage applied. Now, here they've got a whole explanation of what I just told you, and the important part there is this induces a voltage across an inductor, which is also known as back EMF. Now, that is when the magnetic field collapses. You get what they call back EMF. And this may be many times the supply voltage. Remember that the EMF is the electromotive force. And we had that earlier, that term to describe voltage. And that is where the E comes from, that they sometimes throw in to confuse everybody. Now, a car coil works on that principle. They've got an explanation over here, and you put 12 volts in, and you can get several kilovolts across the spark plug. Now, like a capacitor, these inductors, they don't like change. They borrow energy from the circuit and returns the energy to the circuit when the power is removed. So it doesn't actually use power. Now, that is in a perfect conductor. There will always be losses in real life. So there will be losses, but theoretically, it doesn't use it doesn't use power. The value of an inductor indicates how much energy it can store in its magnetic field, and hence how effective it can oppose or attempt to change the current flow through it. The value of an inductor is measured in Henry, and the abbreviation for that would be H, and typical values measured in microhenry and millihenry. The value of an inductor depends on its physical characteristics. Now, these include the number of turns. The more turns, the more inductance. The coil diameter. The larger the diameter, the more inductance. The spacing between the turns. The closer the spacing, the more inductance. Therefore, a longer coil will have less inductance. I don't understand what they're saying there. They say the closer the spacing, the more the inductance. Therefore, a longer coil will have less inductance. Doesn't make sense. I would stop by the closer the spacing, the more the inductance, because that is true. The preamble of the core. Now you can use mild steel as a core. You can use ferrite core, ferrite rod as a core, and that also affects the strength. Since a ferrite core has much higher preamble than air, a ferrite core inductor will have a greater inductance than an air core inductor with the same number of turns. Although the ferrite core inductors have higher inductance than air core inductors, they also have higher losses. So let's just go through that again. Although ferrite core inductors have higher inductance than air core inductors, they also have higher losses, especially at radio frequencies. So if you go into megahertz, then you don't want to have a ferrite core there because the losses are too big. Air core inductors may be wound with a stiff wire, in which case they are self-supporting, or you can use a plastic bobbin as a former to wind, and you'll see that typically with antennas, because the coil that you have at the bottom is not necessarily stiff enough to support the radial that sticks out at the top. So there you'll use a former to wind your coil. Webb made the one antenna with a coil at the bottom out of stainless steel or spring steel, and that works. So they don't have a former, and that makes the antenna a lot cheaper than all the others that needs the former. So uh, um, and it works just as well. Inductance is usually abbreviated as L since I is already used for current.
Excuse me.
So yes,
Sorry. Um, that ferret, it's an insulator, but what is it made of?
that is a good question. Ferrite is iron. Fe is iron. So let's just, I don't know it. I know it's non-conductive, but it is magnetic. But it's is only magnetic at high frequencies. We need Louis for this.
Is that why they say that it could have a problem against like the air one?
Yeah, the air one is
Air one.
has got less losses.
Yeah, because I couldn't understand that. Okay, so this must be like a semiconductor or something, or like you say, in frequency wise.
Yeah, it gives your inductor more inductance at lower frequencies. So, for instance, if you want to build a buck converter or a buck boost converter, the Farad core is good. Um, but if you go to the megahertz, it is not good for that purpose. Okay, there they say iron oxide, 2 ferrite, and 3 oxygens. And this is the same stuff that they used to put on the cassettes, tapes, that the tape material that goes onto the tape that you actually record the music on. And then they obviously use mixtures to achieve different values. Um,
Is the ferrite also not what they use to reduce noise, where they clip it over,
oh,
power cables
absolutely.
and yeah, so that's also, and you'll find them, on your laptop power supplies. So
Correct, yes.
Stefan
So
will have an idea of then what that sort of
that's
unit
it.
is, yeah.
It stops the high frequency from passing through the wire. I don't know whether you guys ever
Oh,
saw when you throw a magnet. They usually do it with these rare earth magnets. They throw it through a copper pipe, and then it falls through the pipe like in slow motion because of the electrical field that it generates in the copper pipe, and that then slows it down because the magnetic field that's generated actually stops it from falling quickly. They've got a couple of YouTube videos where you can look or watch the magnet through a pipe. I think if you just say magnet through a pipe or copper pipe, then you'll come across one of those videos. Very interesting. How magnetic fields interact. I mean, if you throw anything else through the pipe, it falls like a stone, but the magnet goes down slowly. Right. So, but
yeah,
strangely
very
enough,
interesting.
this is
Sorry.
non-conductive. If you and you can also not pick it up with a magnet. You doesn't magnet doesn't cling to it or doesn't attract to it. So
I've seen some people loop the coax wire through it.
correct. We'll get to that still. That's to get rid of common mode currents, because you don't want RF in your shack. You don't want RF where you sit and speak with a microphone, because that radio frequency can start to interfere with the microphone and cause noises and things. So, and they also use that to make the what they call it balance or onions for to match your antenna to your coax to get it down to 50 ohms. For instance, some antennas is 200 ohms, like a dipole, not a dipole, they call it the bazooka something. That is 200 ohms. So you'll have a anon or a balun transformer in circuit so that you can match the impedance. But we'll get to that with the common mode choke, and I've got a few cores lying around here. I mean, once you're in the game, I mean, you use those things everywhere, because whenever you've got some distortion or noise or something, you just slip a core on just to see whether it's maybe that. You happy with that
Yes.
FE203? Oh, no, great. Yes.
I've seen it in, is it similar to those ones that you get like a power supply for a PC?
You'll have a lot of them in there as well. They want to use them in switching power supplies. They've got a certain frequency range. You know, like I said, they use different combinations to have different effects. And at certain frequencies, they are actually numbered. They've got a number, and it tells you they've got a value, and you buy your core according to that value. And some of the guys that do the research with the balance and so on, you know, you do the same balun on a couple of different cores, and then they see which one is most effective and most efficient. That you'll find them in switch mode power supplies, because the switch mode power supply operates in the ideal frequency for those Farad cores. And then of course, when you go to a lower frequency like 50 hertz, like mains, then you have iron in your transformer, because ferrite can't handle that low frequency. And that then makes the transformer more efficient. Happy? Right. Now, like I said, these inductors, they resist change. And now in an AC circuit, the circuit is changing all the time. So when the voltage goes down, the inductor wants to keep the voltage up because the magnetic field is collapsing. And then, of course, when the voltage is rising, the magnetic field must be created again. So yeah, they resist change, or let me say, opposes change. Here they say that it opposes change, and then we get to that opposition to change is called reactance. And it's a lot like the capacitor. It's similar, where it borrows energy from the circuit and it returns it when the energy is reduced from the supply side, and that is measured in ohms, although it's inductance. It's not true resistance, because it doesn't dissipate heat. So the energy is not converted into heat. It's just stored and then returned. And there's your formula to calculate the reactance. The L is obviously for the inductance or reactance equals 2 pi frequency, and then the value in milli or micro or in Henry. So once again, once we've done that calculation, we will get a value in ohm, and we can use Ohm's law from there on to calculate the current that is in that circuit. Now, once again, they've used tens instead of other values. I don't like it when they use ones and tens because it's easy to confuse. But I'm going to pull my calculator closer, if I can put it in a place where we can read and see. Right, for example, suppose we have 1 volt signal at a frequency of 1 megahertz, and it's applied over inductance of 10 microhenries. Now we must calculate the reactance at that frequency. So we're going to say 2 times pi times. Now I'm going to change this here because the 10 to the 6 there is actually confusing. So we're going to take the 1 megahertz times 10 to the 6. I'm going to put that in brackets so that we know that that's a value. And then we say times. Now, here what they've done here is they've taken 10 to the 5. So they moved that one down 1, and they take, instead of -6, they made it -5. My personal way, I don't do that. I enter the thing as it's written. So if it's 10 microhenry, 10 to the -6. Because I just find it easier to do it in that way. And once again, they haven't put the 10 down, so this example is not actually very good. That's why I do it like this. So this 10 is then the 10 microhenries, and that 1 is the 1 megahertz. And then theoretically, if I press that button, we should get to that answer. And we did. That's good. So be careful that you don't get confused. When my daughter was in school and I had to help her with her maths, I said to her, because I said to her, you always write, when you read your story that they give you, as you get your values, you write them down. So you write your voltage down, you write your megahertz down, and you write everything down. And then you use your formula and you do it like this so that you know that your 1 megahertz is that, and your 10 micro Henry is that. It's just the way I do it. I know other people do it, mess around with these scientific notations, but you know what? Once you start messing around with that, your chances for a wrong answer is very good. Right. Is there any questions around this? Right, so let's go there. Now we apply Ohm's law. I equals V divided by the X which we calculated, which is the same as the resistance. So what we're basically going to do is we're going to say it's 1 divided by 62.8 equals. Now that's a technical problem. It is 1 volt. So if I round that, so it's close enough at 16. I wonder if you can.
I just timed it by 1,000.
Yeah,
Then
that's
it
what.
means times by 10 to the 3.
That's right. Yeah, that's so you can do that as well. So if we go there and we go back, and we can say like that, will give us the same result. Now, just for a moment looked incorrect, but looking at it a little bit longer, I realized that it's 15.92, which is close enough to 16, rounded off. If I redo the book, I will put that exactly like this, so that you know that you are 100% correct. Let's get rid of the calculator for the
You
moment.
could also just cheat and do the reciprocal of that answer, 62.8, and then the reciprocal will give you the same thing.
That is very true, but you see, that's where it becomes dangerous.
Oh, is it? Yeah.
Because your voltage might not always be
Oh,
one.
yes, yeah, now I'm with you, yeah. Okay,
You
all
see,
right, scrap that comment, delete that comment.
That's why I don't like when they use ones, tens. They mustn't use, because they get used in other things, and that, well, creates confusion. If that was 2 volt, you would have never said that,
Correct, yeah,
because
now I'm thinking about it, yeah. Okay.
yeah,
Makes mathematical sense.
that's it. Yeah, so I don't know why they did that. Right, the phase relationship. Voltage across the inductor leads the current. It's because, I mean, you've got to build the magnetic field first, and then obviously when the voltage goes down, the current flows through the inductor by, so it's lagging by 90 degrees. Inductor lags the voltage across the inductor by 90 degrees. So there's a 90 degrees phase difference between the voltage and the current. Here they say in a perfect inductor, but we know we don't have perfect inductors, so we will have some losses. Okay, and then they say that it returns to the real inductors made of electrical wire will have some resistance, and of course, where there's resistance, there is losses. A useful acronym, this is very handy, a useful acronym to remember the phase relationship of voltages and currents in inductors and capacitors is the word civil. So with a capacitor, the current is before the volts, and with inductors, the voltage is before the current. in an inductor. Right. To calculate inductors, in series, you just add them together like resistors. And then in parallel, you use the calculation like you do with resistors in parallel. Same principle. So the only thing you have to remember is that capacitors are the other way around. Inductors and resistors calculated the same. Capacitors are the other way around. So let's just get my calculator here. And then we quickly... Right, for example, we've got a 4.7 micro Henry inductor, and that's connected in parallel with a 3.3 micro Henry inductor. Okay, and then if we do that, I don't know why that is there. I tried to figure it out when I went through the lesson before. I don't know why that is there. If anybody knows why those /H is there, I don't know. It's supposed to
Isn't
be
the Hendri sign?
the H, yes, but the slash, I don't know what that
Oh,
is.
it's that.
Because that's a divide, and I don't understand why it's there. I don't know why it's there. I'll try and find out but I think maybe, somebody writes the thing and somebody types it, and that person that types doesn't necessarily know what they're doing. And that's how things like this happen. I don't know. Maybe I'm wrong. Maybe I'm just a monkey and I don't know why it's there. Right. So there's two ways again that we can do this. We can say 1 divided by bracket 4.7 10 to the minus 6 plus bracket. I'm going to put another bracket there just for in case. Then we say I'm busy messing around with myself here now. That one must be there. This one must be out. And this one must be 1 divided by 3.3 minus 6. Now, I don't know why this just doesn't look right. That looks better. I just want to try something out here. Take that one out. That one. That one's got to be there. Right, so that's the one way of doing it. And the other way is, which I prefer, 4.7 times So that's the other way of doing that. And then, of course, if we do that with that, we get that, and we times that by that, and we get to the correct answer. So it's important that a person must know that your micro sign and your mini sign and mega and kilo and all those things, what the scientific notation for each one of those are, because otherwise you're going to struggle. Right, so let's just throw this one to the bottom. Right, summary. Inductors store energy in the magnetic fields. As the current through an inductor changes, it changes the magnetic field in the inductor, and that induces a voltage across the inductor that acts to the opposite of the change to the current flowing through the inductor. So that is called self-inductance. We did see it just now. An AC circuit, inductors exhibit a reactance proportional to frequency. The formula for the reactance of the inductor is. That's the formula. It will be on your formula sheet. We know that we can apply Ohm's law, and by this time we know Ohm's law very well. The civil capacitor I is before V, and inductor V is before I. If you want equivalent inductance, two inductors in series, you add them together. Inductance in parallel, we use the same formula that we use for resistors in parallel. Right. The characteristics of back EMF which a collapsing magnet field causes in a coil is called. Now you guys must answer.
You just read that now in the summary, self-inductance.
That's correct. What is the unit for inductance? I think if anybody don't know that, then
that's almost your name.
that's
Hendri.
yeah. If anybody doesn't know it by now, they shouldn't. They're in the wrong place. Yeah, you know what? When we had class, then you'll sit and you do your work, and they'll explain to somebody else, and you hear your name, and you look up, and you think, "What the hell? Why are you calling my name?" And a few minutes later, when you just get busy, then they say your name again, explaining to somebody else, and yeah, that was very destructive. I mean, distractive. A small air core coil has an inductance of 5 microhenry. What do you have to do if you want a 5 millihenry coil with the same physical dimensions? Right, let's see what can we do. Non-conductive tube and air core is the same, so it would not be A. That could be that. Cannot be that. Donut or toroid will completely change the physical dimensions, so won't be that. The coil must be made out of a heavier gauge wire. No. So we know that to increase the inductance, we must put it wire around the Farad core because that increases the inductance. So that would be B. For radio frequency power applications, with which type of inductor would you get the least amount of loss?
Go with the air core.
Correct. An inductive circuit, in an inductive circuit, the alternating current produced in relation to the applied EMF is
Lagging.
lagging by 90 degrees. That would be A, if I'm correct.
I hope so. That's what I put down.
Yeah, that is indeed correct. And then the next question. If it lags by 90 degrees, the phase shift would be 90 degrees, yeah. Reactance of an inductor. No, it doesn't remain constant. It changes. We know that it increases with frequency. So the higher the frequency, the more the voltage goes up and down, the more upset this inductor gets, and his reactance gets higher and higher because he wants to resist change. And that would be then B. And that's the end of the story. Is there any questions?
I see they didn't put much calculations there, so I'm just wondering were there previous questions with calculations, or did they just leave it out for whatever reason? I don't know. Because even the online test is also only these same 7 questions.
Yeah, you know what? Look, Marty was very disappointed because she spent a lot of time to get the maths right, but really she really put a lot of work in, and she was upset because they didn't ask a lot of math questions.
That's possibly even worse because I think sometimes if you know the formula and it's easier to do the calculation and try and parrot fashion and learn something, like a statement or.
That's right, yeah. So the chances that you're going to get all of this is highly unlikely, but you can get any of it, and that's why I mean, they won't give you impossible stuff. They'll give you simple values like we've got here in this example. I mean, they'll give you typically something like this. So what I would do is I would put other values in amongst the group.
But the question will be more or less written out like that statement above, where you just say, okay,
Correct.
I've got 4.7 and I've got 3.3. I've got the formula. I just do my thing.
Well, that's it. Yeah.
Whatever's
So,
easiest for you, however your calculator works. Now that
well,
I've found out how mine works.
yeah, that's the bigger thing, is actually to know how your calculator works, because some calculators you've got to add 1 times 10 to the, and others you can just type it in, like the one on the screen here. Don't care, but it's easy to figure out, because if you get the wrong answer, then you just add the 1 in, because sometimes that causes the problem on some calculators. And then on your calculator, I don't know whether we're going to actually do calculations where degrees and are going to matter, but you must always make sure that your calculator is set to degrees and not radians or gradients. Otherwise, the moment you start to work with angles, then your calculator gives you the wrong answers. And it's so easy sometimes to. There's another one. Oh, it's the sharp that I had in the photo. That one has got a button that can change it directly. So if you push it by accident during some calculation, you change from degrees to radians, and then you're in trouble. So look, you won't get. I mean, they won't give you like 20 of these values in a row and tell you to calculate. That is exactly like this, just to see whether you understand the concept, or you might not even get this calculation. Any other questions?
Can I speak about something else?
Yeah, absolutely.
Um, Saturday, are you gonna bring some stuff that we can buy from you, like fittings or something?
Look, I myself.
Or are you gonna
You
be
you you
busy?
you mean with the flea market, or coming Saturday?
No, I mean, I know you have a lot of